Today we are going to be talking about constant air volume systems. Years ago, these systems were the norm. Today, not so much. For the same reasons that we have moved from constant speed to variable speed hydronic systems, we have been moving from constant volume to variable air volume systems. And the primary driving factor for this shift again is to save energy. But constant air volume systems still exist to some degree at most of our installations. And there are certain applications where we will never really be able to get away from constant volume systems. This lesson will talk about a couple different configurations of constant air volume systems and describe how they are controlled. The objective for this lesson will be for students to comprehend the common configurations and associated control strategies used for constant air volume systems. The corresponding samples of behavior will be: explain the operation of a residential furnace, define what a constant air volume system is, identify the components of the control loop in a single-zone commercial CAV system, identify the system components in a dual duct system, summarize the operation of a dual duct system, identify the system components in a multi-zone CAV system with reheat, summarize the operation of a multi-zone CAV system with reheat, describe the two control loops in a single zone CAV system which is directly controlling for both temperature as well as humidity. We are going to start off with an explanation of the simplest example of a constant air volume system and look at a residential system. Before we get started, just so we are clear, the air handling unit in a small application like a residence will be referred to as a furnace in this lesson. This might not be the most accurate terminology. In all reality, the furnace is the component which contains a fan and the heating mechanism. Often, the cooling apparatus sits on top of the furnace, but today the whole assembly of a filter, fan, heating, and cooling apparatus will be referred to as a furnace, for simplicity. But why are we talking about residential applications in a course which is supposed to talk about how we control HVAC systems in Air Force buildings? Well, the same furnaces that we install in a residence are often installed in our smaller commercial buildings, and they are controlled in the same manner in both applications. The control mode for these applications is the most simplistic one we have: simple on-off control. These furnaces only serve a single zone. That is, they assume the whole house or small Air Force building they are serving is at roughly the same temperature. They have a single thermostat located somewhere in the space which will provide a representative temperature of the space. Now you might see some bigger homes with two furnaces. Often you can tell this by looking on the side of the house and you'll see two condensing units, each one serving a different furnace. In this case, they split the house into two zones, most likely the upstairs and the downstairs. Furnaces typically have cooling provided by use of a direct expansion coil. That is, the cooling coil has cold refrigerant running through it, not chilled water like we have been talking about in this course up until now. That cold refrigerant absorbs heat, evaporates, and is piped outside where it is compressed, which raises the temperature of the refrigerant, and subsequently expels the heat to the outdoor air. You all should be familiar with the refrigeration cycle, but we will revisit it later in this module. Basically, what I am getting at here is that the cooling mechanism can either be on or off. There is no modulation capability. On the heating side, most furnaces these days are natural gas. Natural gas is combusted in the burner. Heat from the combustion process is transferred via a heat exchanger to the airstream before the air is sent to the occupied space. Again, this type of heating mechanism is either on or off. There is no modulation capability. Alright, so let's walk through a quick example of how these systems are controlled. What the control system does here is simple. The sensor and controller are combined in the thermostat, located in the space. They are really separate entities, just housed together in the same box. The sensor measures the temperature and sends that information to the controller. The controller is programmed to maintain a room temperature, but since this is on-off control, there's also a differential programmed in. Let's say the heating set point is 68 degrees Fahrenheit. If the temperature was measured to be 69 and the furnace was off, it will stay off. But if it is cold outside and the temperature drops, the furnace will kick on when the set point of 68 is reached. When I say kicked on, I mean the fan will turn on, and so will the natural gas burner. The exact supply temperature that comes out of the furnace will vary depending on the temperature of the air entering the furnace, but will probably be somewhere around 85 degrees Fahrenheit. The volumetric flow rate of the fan will stay constant as there is no modulating dampers anywhere in the system. As warm air is put into the occupied space, the temperature will rise. The system will continue to operate until the differential is achieved. That is, the temperature, which is the set point plus the control differential, is sensed back at the thermostat. A typical control differential for a residential system like this is 1 to 2 degrees Fahrenheit. So in this case, let's say the control differential was 2 degrees Fahrenheit. If the thermostat set point was 68, once the room air temperature was found to reach 70 degrees Fahrenheit, the system would shut off. The same concept applies to the cooling application with a residential furnace. Maybe the set point is 75 degrees Fahrenheit. Say the furnace was initially off, and the temperature was measured to be 74 degrees Fahrenheit. If the temperature in the space rose, eventually it would reach a set point of 75 degrees Fahrenheit. The thermostat would tell the furnace to kick on, and by that I mean both the fan as well as the compressor in the refrigeration cycle would turn on. This would allow for the cooling of the air before it is sent from the furnace to the space. The temperature of the air supplied to the space will vary depending on outdoor weather conditions and the temperature of the air coming into the furnace, but it will probably be somewhere around 55 to 60 degrees Fahrenheit. Cool air will be sent to the space and the space temperature will drop. The fan and the compressor will stay on, however, until the differential is met. That means until a temperature equal to the set point minus the programmed in control differential is measured. Again, if we have a 2 degree Fahrenheit control differential, the fan and compressor will be told to turn off when the temperature is sensed to be 73 degrees Fahrenheit. Why do we implement a control differential? Going all the way back to one of the earliest lessons of this course, it is because we want to prevent the system from cycling on and off too rapidly. The control differential is there to extend the life of the equipment, but it also allows the cooling apparatus to run long enough to really wring some moisture out of the air before it is sent to the space. Now, all of what was just described would be how a furnace works if the fan is in the auto setting. Many thermostats allow the fan to be placed in the on position. The control of the system doesn't change much here. Just the fan will always be running. If the space is requiring heating, the fan will always stay on, but the natural gas burner will only kick on when the set point is reached, and it will kick off when the set point plus the control differential is obtained. The fan will stay on even after the burner is cycled off. Same thing on the cooling mode. The fan will stay on, but the compressor running the refrigerant cycle will kick on and off to keep the space temperature somewhere between set point and the set point minus the control differential. Now, some of that was review, or at least I hope it was. You have probably figured out by now how the furnace in your house works, but if not, that is why we included such a discussion. Let's change gears to talk about larger applications of constant air volume systems. Such systems which have modulating capabilities, not ones that just merely turn on and off like the residential furnace we just described. Air systems transfer heat to or from an occupied space. How much heat the system needs to transfer depends on the heating or cooling requirements of the space. The amount of heating or cooling a space needs is obviously going to fluctuate throughout the day and year. It is a function of occupant density, activity, and schedules, lighting, plug loads, the temperature set point you have for the space, the building's construction and orientation, and obviously the outdoor weather conditions. Since the heating and cooling requirements are always changing, we need to have an air system capable of varying the amount of heating or cooling they provide. How much heating or cooling the air system provides can be determined by this simplified equation. I say simplified because this equation truly is an estimation. We encourage you to take some AFIT HVAC design and analysis courses if you want to dive deeper into this equation. In this equation, Q is the heating or cooling requirements of the space in BTUs per hour. V dot is just the volumetric flow rate in cubic feet per minute of the air entering the space. It is also the flow rate of the air leaving the space. Remember, those two flow rates need to be equal, otherwise the building's pressure will build and build until it literally explodes. TSA is the temperature of the supply air being delivered to the space in degrees Fahrenheit, and TRA is the temperature of the return air being sucked out of the space. TRA can also be thought of as the room air temperature, because as we discussed in the last lesson, the room air and return air temperatures are assumed to be equal. So if the required amount of heating or cooling, which is Q in the equation shown here, changes throughout the day and year as we have discussed, we need the air system to be able to modulate how much heat it is adding or taking away from the space. So what variables can we adjust to ensure the right amount of heating or cooling is provided to the space? Well, looking at the right-hand side of the equation, TRA is going to be assumed to be the temperature we want the space to be kept at. So effectively, that is our control variable. That is what we were trying to control for, so we don't want that to change. That leaves the supply air temperature or the volumetric flow rate. If we kept the supply air temperature constant and varied the volumetric flow rate, or CFM, being sent to the space, that is one way we could modulate how much heating or cooling is provided to the space. Or we could just keep the flow rate, or CFM, being sent to the space constant and just modulate the supply air temperature. You might think that a constant air volume system has to follow the last approach, and VAV systems must follow the approach of varying the flow while keeping the supply air temperature constant. However, that is not necessarily always the case. The terms CAV, constant air volume system, and VAV, variable air volume, are referring to the total airflow moving through the system. There are CAV configurations in which the total airflow in the system is constant, but the airflow that goes into the various spaces is modulated. And there are constant air volume configurations which modulate the supply air temperature being sent to each space, all while maintaining a constant airflow to the space. This might sound a bit complicated, so let's look at a couple of these different configurations of commercial-sized constant air volume systems to see how this all would happen. Let's start simple and work our way up. Here we have a single zone system, very similar to what we saw with the residential application. You might still see a single zone system in larger facilities like a warehouse or a large laboratory. In this system, it is not going to turn on and off like we saw in the residential system. Instead, the fan is going to remain on all the time, and the supply air temperature is going to be adjusted in order to maintain the temperature in the space. With the hot water and chilled water system shown here, we now have the modulation capability back at the heating and cooling coils by use of our control valves. So this is pretty simple. You now have a simple closed control loop. The control variable is the room air temperature. If that sensed temperature rises above the cooling set point of, say, 75 degrees Fahrenheit, the controller would know to send more chilled water through the cooling coil. The control valve controlling the flow would modulate to try and maintain that 75 degree Fahrenheit in the room. As the seasons change, the cooling requirements might get less and less. The temperature will drop below 75 and the chilled water control valve will start to close. If the space temperature keeps dropping, even after the chilled water control valve is fully closed, that would be a good indication that the system no longer needs cooling. Eventually, the temperature will continue to drop until it reaches what is defined as the heating set point. This may be 70 degrees Fahrenheit. If the space temperature continues to fall below 70, then the heating coil's control valve will engage to try and maintain 70 degrees in the space. Notice the heating and cooling control valves are both controlled by the same controller. They have separate set points, however. There needs to be different set points to prevent quick cycling between the two valves. If both the heating and cooling set point were at 75 degrees Fahrenheit, any drop in space temperature below 75 would tell the chilled water control valve to start closing and simultaneously tell the hot water control valve to start opening. The two different hydronic systems would be fighting each other, and we would be wasting energy as we would be heating and cooling the same air before we sent it to the space. I don't care who you are, that's just dumb. So that is how we might control a single zone system. But it can get more complicated when we have multiple zones that have differing heating or cooling requirements and potentially different room temperature set points. Let's see how we can address those obstacles. The first option for multi-zone constant air volume systems would be that of the dual duct system. In this configuration, we have the supply fan push air down two parallel ducts. One is called the hot deck and the other the cold deck. The hot deck has a heating coil to keep the air traveling down the duct hot. Big surprise. That coil's control valve modulates hot water through the coil to maintain a constant temperature of air just downstream of the coil. And that temperature might be something like 85 degrees Fahrenheit. Same thing in the cold deck. There's a chilled water coil, whose control valve modulates to maintain a certain temperature of air just downstream from it. That set point might be something on the order of 55 degrees Fahrenheit. The airs are then pushed down the respective duct paths, or decks, until they get to each space. Each space has a dedicated mixing box and a thermostat. The mixing box typically has two dampers, one on the discharge of each deck. The thermostat in the space measures the space temperature, compares it to the room temperature set point, and adjusts the dampers in the mixing box accordingly. If the room temperature is falling below set point, that would indicate slightly warmer air needs to be supplied to the space. Thus, the hot deck's damper in the mixing box would open a little bit more, and the cold deck's damper would close a little more. Going back to that equation which quantifies how much heat the system is adding to or extracting from the space, you can see that for dual duct systems, we are implementing the second control option of keeping the volumetric flow rate relatively constant and just modulating the supplier temperature of the air being sent to the space. Such a control loop occurs at each of the zones. Thus, it is possible for Zone 1 to be in cooling, while Zone 2 is requiring a little heat, and Zone 3 requiring a lot of heat. Constant volume dual duct systems provide the capability for good control and flexibility, but as you can imagine, they consume a ton of energy. Look at the path of the air going through the hot deck to the occupied space. We are paying to heat that air up, but then we cool it down. Similarly, if you follow the air going through the cold deck to the occupied space, we are paying to cool that air down, only to heat it back up again at the mixing box. Additionally, just the fact that they are constant air volume, CAV, we will never see any fan energy savings at part load scenarios like we would see in VAV systems. These systems are becoming less common, but they still exist, even in the Air Force. I will say this, there are ways to retrofit these constant volume dual duct systems into variable air volume dual duct systems, which would inherently save some fan energy. However, such a retrofit gets complicated very quickly, and describing how this would look is a little beyond the scope of this course. A more common configuration of constant air volume systems in a commercial application is one that implements reheat. In this application, we have just one duct path. Back in the air handling unit, there's a cooling coil and a heating coil. The control valves on those coils are controlled to maintain a constant supplier temperature leaving the air handling unit at some set point. So there is the first closed control loop, right there in the air handling unit. The control variable in that control loop is the temperature of the air leaving the air handling unit, and the control devices are the chilled water and hot water control valves, which modulate to ensure we maintain that temperature set point. A typical set point here would be between 55 and 60 degrees Fahrenheit. In this system configuration, a constant amount of air is constantly being pushed to each respective space. Zone 1 might always be getting 1000 CFM of air. Same with zones 2 and 3, but for us to control to a specific room temperature in each space, we will need the ability to adjust the supply temperature of the air being dispensed to each room. In this system, we can adjust that temperature by running a reheat coil in the ductwork just prior to the supply air diffusers for each respective room. That reheat coil could be an electric resistance coil, which could only be staged on or off. Thus, it would be exhibiting an on-off or two-position control mode. That reheat coil could also be a hot water coil, which is capable of modulating control by use of a modulating control valve, which dictates the amount of flow going through the coil. So there again lies another closed control loop for each space. The room air temperature is the control variable, and the control device is the reheat coil's control valve. The manipulated variable can be thought of as the temperature of the air being supplied to the space. Each space can be controlled to a different temperature set point if desired. If a space is requiring a lot of cooling, we may not engage that reheat coil and just supply 55-degree air to that space. Another space may be requiring a lot of heating. Thus, it would fully engage the reheat coil to supply maybe 85-degree Fahrenheit air. Or the space may need neither cooling nor heating. Thus, we only slightly engage the reheat coil until the supply air temperature matches that of the room air temperature. So this system configuration uses a lot less ductwork than the dual duct system. It is still energy inefficient, however, because for the spaces requiring heating, we are still paying to heat up the air that we just paid to cool down.